instead of an input force acting on our system, we could instead have a prescribed displacement or an input displacement acting upon the system. Now, in reality, this displacement is being caused by a force. We just don't know what that particular force is. We are saying that we want this exact displacement acting on one end of our system. So indirectly, this will be causing forces in our system. Because as we see, if we're prescribing the motion of this base, as in here we're going to stick with a sine or a cosine function, by this base moving up and down, it's going to be stretching the spring, which is going to be applying a force on our mass, and it's going to be stretching the damper, which is going to cause a force on our mass. However, as our input, if we say y of t is our input, and in this simple case, we're just going to say it's some constant amplitude times a sine function, so some periodic displacement happening at the base. And when we look at from a free body diagram perspective, that mass is feeling that force from the spring and force from the damper due to the relative displacement and the relative velocity of the damper. So if we go from the free body diagram to the equation of motion, we see that the force is going to depend on our x and our y, the position of our mass and the position of our base, but also the velocity of our mass and the velocity of our base. But again, we know what y is because we are going to be defining it here. So finding y and putting it into this equation and y dot and putting it into this equation is pretty straightforward. So what we're going to be interested in is, what is the solution to this equation of motion for x of t? So we can rewrite our equation of motion by putting our dependent variable on the left and our independent variable on the right. So notice here, because we had that definition for y of t, I can move that to the right-hand side because I now have explicit values with t in it on the right-hand side. We're operating at that amplitude, capital Y, and then we have constants k and c omega also on the right-hand side. And our left-hand side looks like it has been for the other types of damped systems. We have our m, our c, and our k. So I'm going to take this sine and this cosine. Notice that they have the same frequency here. And like we've done before, I'm going to combine the sine and the cosine into one term, in this case a sine, and it's going to have a phase alpha associated with it. And then I'm going to combine those amplitudes, and I'll call that A. So I'm going to express the right-hand side now as this amplitude times a sine function with a phase involved. So it looks pretty similar to what we saw with the prescribed forcing before, although we do have this phase involved. And we'll be able to calculate that amplitude based on given parameters, so the amplitude of our prescribed displacement, and then system properties, the spring constant, the damping coefficient, and the driving frequency. And our phase is going to involve, again, the driving frequency, it's going to involve the spring constant and the damping coefficient. So we can get the total solution out of this. We can get the steady state solution out of that as part of the total solution. For this course, we're only going to look at the steady state solution. I'm not going to go into the total solution and worry about initial conditions. If you're interested, you can look in textbooks on the subject or papers on the subject. It's just out of the scope of what I want to cover in this course. So the particular or steady state solution is going to have the form of this x sine omega t minus phi. So at steady state, we are going to be oscillating at that same input frequency, but our amplitude and our phase are going to be different. So largely, it looks like what we should expect from any forced system that's driven at constant frequency. It's just that calculating that amplitude and phase is just a little bit different when we have a prescribed motion or a prescribed displacement. So with these formula, we're able to calculate the output amplitude x and the output phase phi. And then we can construct what the steady state solution looks like for a prescribed motion. And finally, we might also talk about what's called the transmissibility, and that is really just a special term for the ratio of the output amplitude to the input amplitude when they are the same type of amplitudes. Like in this case, our output amplitude is going to be a displacement, but also our input amplitude is a displacement. So we can talk about this ratio in terms of the transmissibility. is the transmissibility less than 1, equal to 1, greater than 1, is how much amplification or attenuation is there from the output versus the input. Really, the transmissibility is just a special form of the magnitude that we were looking at before, the ratio of the output amplitude to the input amplitude. But in previous times where our input was a force directly, then that magnitude was a displacement divided by a force. Here, our output is going to be a displacement and our input is also a displacement. So because the types of input and output match, we can call that the transmissibility.